history of the synthetic aperture radar. Before United States, they developed the field. It is the first one. In 1965. Then it is, I think, the military one, expert. Then they developed the CISA to monitor the ocean area. But this satellite is just around 6 months. 6 months, and it's very big. It's very huge satellite. And working in airband with the polarization is H. Then after that is Russian or Soviet. Soviet launched Cosmos 1874. Then Almaz 1. The famous one is Almaz 1. Then Europe, yes, ERS 1. Then ERS 2. Then Japan. It is I think almost same. Yeah? Japan Earth Resources satellite. One, yeah. But unfortunately, no just 2. Yeah. Now they change to be errors. Then radar sat is Canada. Then F2, yeah. Then they made the tandem monitor. Then Pilora, this is Russia. I collected this information. Maybe you cannot find in the books. Yeah. And then is RTM and PSAT, and it is the Japan one. It is for the information gathering satellite, like spy. And you can find the spec. Then LS Parsat, yeah. And next LS Parsat 2, I hope next year. Yeah. Then China launched Yaoga 1. Yes. I think it is multi-polarization, and it is the spy satellite version of the China. And then they launched many spy satellites. Yes, Taiwan one I told you. It's too selfie because they use airband, but very how is their data cheaper than other countries? Spy satellite. I think you cannot find this. Spy, and then Salupe also military one is made by Germany, and the one is 5. Then Condor E in China is almost. And this check here. L-band, X-band, S-band, sometimes C-band. And they're working in X-band. And I think in the world is L-band, S-band, C-band, X-band. It is the common one. And it is depend on what you want to see. If you want to see the forest, yes, I think it's better using L-band, low frequency. But if you want to find high resolution and just the surface of our Earth, I mean the surface is including the surface of the canopy of the vegetation is X-band, high frequency. X-band. X. Okay, yes, also the Japanese information gathering satellite, and you cannot find this data in the common one. And Yaoga, Cosmos, yes, Skymet, then Terasa X, yeah. And Salupe, Germany, yes, they are 5. Then Cosmos Skymet is Italy. It is also nice resolution. Yeah. 3 and okay, Radarsat 2 is Canada. Then okay, you can find here, and Texat 1. It is the spy satellite of the Israel with 1 meter because they use spotlight. Spotlight spotlight is one target like this, and they monitor, like this.
Oh, one location only.
In one and failure. If you transmit and scattering from one object in the long time, you can find high resolution. And this is the reason I want. And then Germany. It is Salupe and the 5. And hence Chandrayaan 1 is Minisar is the satellite itself is India, but the SAR center is John Hopkins University, America. And they launched a satellite on the sensor for the moon. To monitor the moon's surface to find the water, using the circular polarized. But Minisat is very compact. It's not the real circular polarized, but they use the linear polarization antenna too, and the phase they change 90 degrees. Phase change. To generate the circular. Okay, and I think many. And now I developed this one. It is in my laboratory. We work with the Indonesian Aerospace Agency, and I hope also the Malaysia. We can develop our own. And now I also together with the ISA Jackson and the Korean Ajo University to develop the same satellite. We hope we can launch 5 satellites to monitor, for example, one area, frequently.
There's any law regarding how many you send? People sending satellite. Is there a restriction for countries to do that, or is it open?
You can see here, the CPSAT, circularly polarized synthetic aperture radar. I think it's no satellite. No satellite. It is the first one. I hope we can launch the first one in the world.
But I thought you were writing on another satellite. Like
another satellite is for the ionospheric monitoring. I will show you later in this slide. You can find. Now we propose 2 types of satellites. One satellite for the ionospheric monitoring, and another one is for the land surface monitoring. I hope I can get the budget next year. Next year. Oh, okay. If we compare with another satellite, you can find here the weight. How many tons? And my satellite is 100 kilograms. It's very cute. And then polarization. Polarization is linear polarization and circular polarization. And the power. Power is how many kilowatt? And our target is maximum 300. Now we consider many technology to reduce the weight, to reduce the antenna, to reduce the processing, sound signal processing, and the memory. Oh, we must consider many. And I hope we can prove this one as we start next year. And half budget from my side and half budget from Indonesian side. Okay. Okay. The trend of the spaceborne sound. It depends on the application. And here, like I already explained to you, it is the band, the frequency. P band, L band, S band, C band, X band, K band. And here the resolution. The resolution. If the low frequency, I think the resolution also, rough. Our target is using the microsatellite is 30 meter for large monitor. But if you want to increase the resolution, you can increase your frequency, or use the technique spotlight. But spotlight is, it's very difficult, because it mechanically, spotlight or what is electrically, electrically means use the beam, steering, beam steering, It's our system will wait if we increase some function. Okay, and you can find some application here. So what you want to monitor? If you want to monitor the urban area, I think it's better in this area. L-band to X-band. Or for example, forest area, I think better use L-band. So when you decide your mission, so please consider what kind of mission and then what frequency is the best one. Of course, you can also monitor the forest area using X-band, but scattered by your canopy. You cannot penetrate your canopy. Okay. Then it is also the vision and the trend. Our target is here. Then you can find the terasal accuracy, X-band, and resolution is 1 meter. Our target is here, around 30 meter resolution, working at camera. So when you meet your vision, so please listen. And then okay, this is almost it. And this is the vision of our microsatellite and CPSAT. Now we develop with MMU for CPSAT together, and I hope in the future, in the near future, we can use this basic system for our microsatellite. For the design, we already almost have the design for the microsatellite. And this satellite we want to employ is for the basic experiment and application. Basic experiment is the scattering mechanism from the circular polarization. From the circular polarization, we can derive the linear polarization, circular polarization, and elliptical polarization. Then from this scattering, we can classify what happened in our Earth. And I hope we can also learn to another planets in the future. I think we just can observe some planet, but we have mapping the real surface. I hope we can use this radar to mapping the planet, and we can move in the future and find new material to develop. I think maybe we can develop the new type of airplane, rocket, and maybe we can find a new fuel to make more faster, to moving, Okay, and maybe like Columbus, in the future. But we need a sensor, a good sensor, to monitor our universe is, Now we must consider. Right now we develop the synthetic aperture radar. I think the best one in this century. But I don't know, if we go to another planet, maybe we can find another material and we can develop another sensor, a good sensor. Let's try. I don't know. I can, maybe I am already died. But at least we start. And okay, we can also use the circular polarized for the interferometry, and we can also generate the axial ratio image. Axial ratio image is, from the circular polarized or the elliptical polarization, we can generate the axial ratio. From the axial ratio, like this one. Here, A and B. From the A and B, the major axis divided by the minor axis, you can find this axial ratio. This from the axial ratio of the scattering wave, so you can generate new one, new image. Maybe I think it is the new one. fine rate. Okay. You can generate the H ratio, and you can also generate the tilted angle. Tilted angle or the this one, the LPCP. LPCP. For example, oh, it is scattering from the mango. Yeah? Mango tree. Oh, the scattering is tilted angle is maybe different when we monitor scattering from the what is it? Another tree. Okay? So we can make a classification. Oh, this area is mango area. This area is sawit or coconut. Yeah? Coconut area. Yeah? Based on this new information by using the circular polarization. Then application. Okay, I think many applications, and I'm already made some research by using some information of synthetic aperture. And it is the bus of our system. Satellite bus is composed by the altitude control system, because we must, control where is the position of our satellite. Because velocity is 7 km per second. It's very fast. Yeah? So, and we must know the exact position. If we don't know the exact position, because to generate the GEM, we need the baseline. Yeah? Baseline from one position to another position. Yeah? If possible, is for example, for aerospatial, maybe less than 400 meter, okay? 400 meter. Okay? But within 1 second is already 7 kilometer. Okay? Yeah. So we need high precision. In this case, is we need the GPS, yes, magnetro. You can find here, yeah? Electromagnetic flow, yeah? Then GPS receiver, and sun sensor, magnetometer, yeah? Fiber optic gyro, and many. Or reaction will, to control our satellite. Because when we put our satellite on the orbit, yeah, I think our satellite is not look like straight, but actually like a slit, like this. Yeah. Yeah. So I think the track is moving. It's moving like this. The beam, yeah? The beam of our satellite is cannot strike like this one. Yeah? It's moving. So we need when here is we need move and this one the beam. How to control? Use many devices.
All this is develop yourself or you
So we need high precision. We cannot do by ourselves.
it was quite costly.
Yes, we have some collaboration with many companies, yeah, who develop this EMT or GPS, high precision GPS. You cannot use your car navigation.
So we currently also develop our MMU own one part.
So we need high precision one. High precision, and the price is maybe one is you can find a Ferrari.
The position of the satellite.
Okay, this is the altitude control system. Then the power. We need the power, especially for the synthetic aperture radar. We need big power, to transmit. In our case, it's 300 watts. Yeah? 300 watts. Maybe we cannot observe continuously. Yeah? We save the energy on the power. Then after full, then we transmit. Yeah? We need a scheduling of our power management. Yeah? Then telecommunication to send the command and to send the data to the ground. Yeah. And then here it is the onboard computer to control all of our system. And here's some sensor. Part is we developed a CPSAT now in our project with CPSAT. Then GPSR, now I'm working with Tokyo University, yes, for the GPSR, and GPS occultation, now I'm working with Kyoto University. Yeah. And this Spirit satellite. And this for the CPSAT, for the transmitter, now we use the chirp pulse unit, yeah, chirp pulse, then we transmit, then scattering, and we receive together here for the left-handed and right-handed, and together then we process. We develop our antenna, and now for the system we work together with MMU, yeah, and company RMK for the high power amplifier. Okay, and this is our after launch. I hope now we still make some modification because the antenna actually we did a very large antenna, but now we want to reduce the antenna. Yeah. I hope we can reduce just one. Now we try. Yeah, we try. Yeah. Now we work together with Tokyo Institute of Technology to make the antenna more small. Yes, and if we use this large antenna, yes, if we use the large antenna, so how to reduce the weight to be light antenna? Now we also have collaboration with one company to develop the carbon composite. Carbon composite one to reduce. Then, for example, this antenna is, every square meter is just 300 grams. It's very light. Because our total satellite is 100 kilograms. 100 kilogram satellite is very, very difficult to realize. And many people now have a competition to realize a 100 kilogram SAR on board microsatellite in the world. Yeah. But who is the winner? I don't know. That's right. Yeah. I hope we are the winner. And yes, we, it is our ground station, and I hope we can also work together with MMU or USM UNITEM if we launch and we can receive our data and we can share together. Okay, this is the development. Yes, how to make the system is more light and compact and smart. Yeah? It is many people try to make a big satellite but low weight. Yeah? Low. Yeah. So we need smart material. Smart material. I hope in the future we can go to another planet and we can find more light material. But first is how to monitor the to mapping another planet, the most important. Because when we landing, we landing to the another planet, we need to know the environment of the planet. If we go, but suddenly we know that the gravity is more bigger than our planet. It's very fast drop. Yeah? We destroy our island. Yeah? So we need to make some observation. And how to reduce the weight of spaceborne is, I think, many researchers now try to find the material and technique. And also when we want to launch our satellite, we need to put on the capsule of the nose of the rocket. How to put the safe one? Yeah. for example, for our single aperture radar, we need this very large antenna. We cannot, put in the install condition that large. The antenna will destroy. Okay? Because the speed of the rocket. Yeah. We need to fold it. Yeah. Then launch. Then after that deploy. Or to deploy our antenna is also another topic. For example, this one is the sunflower or the umbrella type of the antenna. And then it is another deployment system for the CISA. They put the phone in, then launch, then release, deploy. And especially now we develop the synthetic aperture with the circular polarization. For the linear is, I think, is easy, yes. But circular is very hard, yeah. Because when we launch, then if our antenna face to the sun, yeah, when the temperature is 250 Celsius degree, yeah. 250, I think chicken is burnt. Yeah. Our antenna is also, yeah, it's very dangerous. Yeah. And our antenna will expand it. But when our satellite will, through the night time of our opposite side of our Earth with -50, -50 to our then 250 degrees, 2 hours, frequently, yeah. Burn, freezing, burn, freezing, yeah. Burn, destroy. Yeah. And the effect of the radiation, yeah, we must also consider. Yeah. So, circular polarization, if just some micron change, our antenna change some micron, so the circular polarization characteristic will change. Yeah? So if the circular polarization change, I think our image will change. Yeah? So how to design the antenna part is also important in this. Many problems, but we must solve.
But your lab will get a wide variety of things, right? From antenna to the satellite design.
Yeah, we try to cover all. Yeah. I think the complete one in Japan. Yeah. Yeah. Like department stuff. For some. But yeah, we need many people to join in this research. Yeah. So why now I collaborate with many companies and many research agencies, and then we divide the duty, yeah? Job, yeah? Yeah. And my duty is to collect money. I hope next year I can get big money and can yes, to develop the UAV sub, so we spend much money.
You need mechanical engineer.
I collect money and then, because in my life I have a time mark in my life. And I must finish my PhD 30 years old already. Okay. And then I must
Send satellite by
yes, develop the UAV before 45, but I'm already realized 42. Yeah. And I established this my laboratory from 34 years old. Yeah, when I'm 34 years old, and my target is 40. I must complete all of my laboratory, and I'm already complete 38 years old. Yeah. Then now after UAV finished, my target is 50. Yeah. Before 50, I want to launch myself. Yeah. It is my time. I hope. For that. And after that, I want to take a rest. Okay? Yeah.
the novelty?
It is just a bonus.
Bonus.
Our target is for human, for human life. If we give many people happy, I don't know. I think Nobel is not so big. If in my case, if many people happy, okay, it is I'm satisfied, and maybe I can die with happy. Okay, it is okay to make to reduce the weight is many planning of antenna. One is the inflatable antenna. Inflatable. Even like our clothes, it's we can fold. But the problem is like this one. Yeah? Our antenna when we launch and deploy open, we need strong. Strength. Even 1 centimeter different, it is will affect to our image because the beam will change. If possible, it's flat. So it is how to make the flat antenna on the topic when we develop the inflatable antenna. It's very light, but also how to select the material for the space. It is also another topic. I think it's many type of the inflatable and it is developed by I think NASA. And okay, I want to talk about my research. In my case is when I'm child, my dream is to develop the aircraft. Yes. Then radar. Yes. It is because my father is the Indonesian Air Force. Yeah. Yes. And almost every day, I face the radar. Radar and okay, in my stream, maybe another people have different experience, but in my case it's because I face every day the radar, and I taught my father and another staff, and it is made by Indonesian. Yes, no, it's made by overseas. So then I must develop for just my country. In this time, yeah. Then I try to develop my own radar. Yeah. Then also the aircraft. Then why when I'm graduated from the high school, I want to apply for the aerodynamic of the aircraft. But unfortunately, I received a scholarship to learn in the Department of Electrical Engineering. Different department. Because it is the duty from the country, because I received the scholarship from my country. Then I learned to the Kanazawa University, the Department of Engineering, then Electrical Engineering, but I could not forget my dream. Then I want to find the laboratory who can develop the radar. Then after that I started to develop the radar, but it is unfortunately also the radar it's not for the aircraft, but for the underground. Okay, no problem, underground. Then I started the underground. Then when I enrolled to the doctor course, I want to find also the aircraft, but I could not find. Then I find in the center. In the center, then no professor is expert in radar. Then because it is in doctor course, so I want to do my dream in my last education. So nobody can supervise. I do by myself. Then I started to develop this in the basic research. Then I continue in my laboratory. I started to develop the synthetic aperture radar and unmanned aerial vehicle. Then later the microsatellite in my laboratory. it's almost my dream. Yeah. Okay. So in this case, you maybe you know you cannot find your dream in your education period, but no problem. Yeah. You can continue after you finish your education. It is just my experience. Yeah. Then yes, I realized the unmanned area vehicle. Then now we together with MMU we realize the synthetic arena. Yeah. Then I hope for the sun. Yes. I hope before 8 years later. Now I'm 42. Yes. I hope before 50 we can launch our sun. Okay, this is just my biodata. Yeah. Then our UAV now is the payload. We can put the payload is around 20 to 25 kilometers. Yeah. If you're 25, you can fly. You can like this one, yeah? But another guy. Right.
Cepat masuk.
25.
I know.
You're the candidate.
Opposite class. Opposite class another more.
So we need two UAV. Okay. And the total weight is almost 150 with the okay, the wingspan. The wingspan is 6 meters, and the length is 5 meters. I think this UAV is the biggest one in I don't know, maybe in Asia. Yes,
You design your own or you?
We designed together with the company, yes, and then because if you can see this shape, the shape is we designed for our radar.
Okay. Especially to cater your equipment.
And then we want to put many sensors. The synthetic aperture radar, our radar, then GPSR with the Tokyo University, and GPSR with the Kyoto University, and another for the monitoring of the volcano or the gravity. We also put the gravity, and if the nuclear plant blow up, so we can put here the radiation monitor. Last time we want to do the monitoring of the radiation, but unfortunately in Japan we can just fly 150 meters. We cannot go higher.
More processing lah to take care of it.
Yes, last time we made the experiment. So I want to show you. Maybe you already see in my YouTube. Yeah. In the YouTube, as you already see, but what kind of experiment is not explained. Because last time is here's the Mount Fuji, yeah. And there is the Pacific Ocean. Here's Pacific Ocean and Fujikawa. Yeah. Actually, we plan to make another flight this month or next month, yeah. But now it's Fujikawa. Here's the river of Fujikawa. No, they made the to build, yeah, renovation. So we cannot use this.
River restoration.
Yeah, to make, here's the river. Yes, the river, the water is from the Fuji.
River restoration.
And we cannot use for until maybe February or March. Okay, we put here the IMU, GPS, and many instruments, and we need to, calibrate. We turn 360 degrees, twice or 3 times.
Oh,
Sure.
Like if you buy the iPhone, you need like this.
Yes,
It's almost same.
If we go Hokkaido, can we fly more than 150 meters? If we go other place, meaning Yeah, if we go other place, can we fly over 150 meters?
I designed for 4 kilometers.
But Japan, most Japan cannot go there. Many airplanes here.
Maybe Malaysia, Sabah, Sabah area,
We can fly out.
200 meters.
7,000 feet. Last time we have one mission.
1 kilometer.
11,000 3.5 about feet. But we may get a flight permission.
There is flight permission. When
From
start the flight permission, less than 200.
How far you can go? How far you can go?
Far is depend on the automatic. Okay, we can fly 6 hours when the speed is 150 kilometer per second per hour. Yeah. Okay, run 700 kilometers.
Yeah.
We can go. Yeah.
Dia boleh
Maybe
AM boleh ni inspect line tak payah hantar
from
orang.
Sabah to
Pakai UAV.
I don't know from
Cross
the
based on the antenna.
but we need high precision navigation. Okay, this is check the engine and the driver can go straight or not. Because if for the parking and for the landing, must start and turn 360 degrees. And we use the engine is 275 cc. 75 cc. I don't know. Small car. Bike is maybe 100 cc.
Oh my God.
Bicycle. Yeah. Now impossible. Yeah. You want to upgrade. Okay, we can test roll. And next, we test for the what is running for the running. And the pilot is inside the car.
You have to
We must
follow.
close to the
Why?
UAV. For the first time.
For the first time.
It is the pilot. At least we need the most important three experiments. Running, take off, and low flying, and then is the real flight. First is running, can go straight on and running. Here we design if 120 kilometers per second will automatically take off. They take off automatically. A big jumbo jet, if the speed is you don't need it, you will take off. Okay, it can running. Then next is take off. Take off, then landing. And it is the most dangerous. But take off, if landing we cannot control it. Crash.
There goes the fire rate.
Just 10 million yen. From 10 to
I want to be responsible.
10 to
Oh, I need that. I've never seen this.
Tak cakap
it is very slow.
kalau tunjuk kat data wiki minat. Mahal sangat ni. Cakap bagus.
It is slow.
I'm not questioning about me, but take tempat land. Dia tak boleh land dekat food kan.
Where we can do the experiment at Malaysia.
Basically, not because
Why don't they do
flight
high
condition is not easy. Where the top will be
Because you need runway.
Malaysia,
is take off. Yeah. Take off.
And then B.
Like this one.
That's landing?
So we must, keep the weight. Yeah. Maybe accident like this one. Okay, then it is take off, then low flying.
Dia cepat belajar tak? Dia tahu, oh macam ni kena hitam.
Okay, low flying.
Oh, you flying.
Overshoot.
Okay, because after that is Pacific Ocean. The wind is very strong.
Oh,
Jangan titik pada
I think we need like this.
okay, this is
Okay, it is the real. After we say, oh, can fly, yeah. Oh, and then the pilot is ask me, so, yeah. Please give time to fly. Actually, our experiment is just 3 experiments finished, but he asked me to do the real flying. Okay, this airport is just 800 meters. 800 meters. We designed for 1 kilometer.
Berapa lama di sini tu? Kita nampak cara orang management.
It's very small. And we can fly just 350 meters. We designed for 1 kilometer, but we can take off just 300. And then we can landing for, we need just 200 meters.
Once you lock the route, you will go straight. I mean, it's out of the radar, out of the remote control. Automatically go
In this case, it's manually.
manually. Let's say you want to go to like 300 kilometers. So once you get the your magnitude, then you just automatically.
We developed the autonomous pilot system. Yeah. So next year.
Then it will
We can
turn back.
put and yes, for the take off, then turn some, then automatic, and then go.
Where you want to scan the.
oh, and then go back.
Then after that is back. Then
Because
if no,
you cannot see the aircraft walk. 300 kilo, right?
even 1 kilo is you cannot see. It's so small. It is 6 meter, but 1 kilo is is small. Even it is it is just maybe 200 meter. Yeah, it's so small. Yeah. Okay, we made 5 times turn. Then we landing. But the voice is good. Yeah. We want to put some sensor on the left side and right side. Last time we forget to put the cover. It's dangerous. Because we didn't predict for the flight. We just test it. Then we forget to put the flap on our wing. If we put for long flight, will broken. Because when this wing and the main wing, we put here the joint. We need to couple. Okay, next is we prepare for simulate to landing. because we cannot landing directly.
Yeah.
We simulate can go. You can control, through the landing field. That is for the real. Okay, next. This, suddenly.
Oh.
With the speed, it may be more than 150.
Too fast. Laju ya.
But at least, the pilot know how to, to approach to the airport on the landing. And next, okay,
Tak boleh landing macam ni awak tu.
I think it is good reference for you. I think if you do like this, it's not easy. Many people is crash. First flight is crash. It is common.
Ini a license in Malaysia tu.
Yang kecil pun crash.
Ini is a license. Japan ni pun is a license.
Because the pilot is from the Jaksa.
Dia lah cakap pilot.
It's very
Tak rasa. Sekarang tu.
so many people is just me. I cannot speak because if crash is my responsibility. Okay, yeah. Finish this. And for the landing is just 200 meters.
At the moment, how many you have?
Yeah, two.
How many aircraft?
I have one, and next we prepare for another one. Yeah. Okay.
Jet fighter.
Yes, the pilot. Yeah. It's big. Yeah. One guy can put inside.
One child.
Now I wonder, yes, the wing, because many times, then the impact of the weight and the weight of the body, then like hold it. Now we made some improvement for this system. Please remember, please make 3 times treatment before you.
Boleh? Saya buat turun Hanafi. Boleh? Buat turun Hanafi.
Dia boleh rekam.
Stable.
Every time.
Dia mahal.
Because yes, we have a recommendation from the pilot, especially if you want to launch big aircraft. Big aircraft is very expensive, and we register the insurance for this aircraft.
Of course.
If accident and destroy the house or not the facility, we can recover 100 million. Yeah. 100.
That is third party insurance or it covers the
Our system? No, our system is zero.
zero right?
You will have your mistake zero.
Zero.
Liability lah.
Third party.
But for other people who
Kalau kena orang
die,
lain rumah,
accident, go to the hospital, they will cover 100.
they are high risk.
For our service, because it's high risk, it's crash is common.
But your CPs we can mount on the light aircraft also, right? Let's say if we want to test it in Kota Baru, is it possible? With light aircraft?
Use this one?
No, light aircraft. With the
Just now.
Just now, okay.
Just now.
Let's maybe
That's
maybe
easy,
we can use man. Yeah,
That's easy.
it's not unmanned, but
Man can, no problem.
no problem. Man, no problem.
Modify it.
need
This
to
one
check
is
many authorization level. They check already to bring in Korean UAV.
No,
Yeah.
not Korean UAV.
Cessna,
That you
Cessna.
never know.
Cessna, yeah.
Put it on a light aircraft. Like
One of our alternative is use Cessna.
yeah, I think that is a potential solution.
But if Cessna is, we need, airport, yeah.
Yeah,
Defend the airport. But
we have to
if
plan.
is if we want to monitor is far away from the airport, we
Kota
cannot
Baru,
just
there's
use
airport.
Cessna.
Kota Baru.
Yes, we can just use Cessna or helicopter.
I think we make mistake. I think
Yeah, if they we can use another day.
I think it's not so expensive.
Rantes lah. Rantes na. Sebab kalau UAV tak boleh masuk kan. UAV kalau
And my son also doing the
Sama
glide.
sekali. We try activity on JICA also.
For the circularly polarized synthetic aperture radar, we put two antenna, right-handed and left-handed for transmitter, and two antenna, right-handed and left-handed for receiver. Transmit and scattering. Then scattering from two information, you can generate the analytical polarity. Yeah. Then from here you can generate many information. Okay, it is when we make experiment of our UAV, yeah, with Harasan. This is our pilot, and me and my student here. And okay, it is the first time when we made experiment. We brought to the Otone airport, yeah, different airport. When we install, what happened? The propeller is opposite.
It's small or what?
We put here is must push, yeah? Push type. But we got the propeller is for the, pull, yeah? Pull. So it's opposite. So our UAV is not there, but here. We prepare how many months? Just a simple. So after that we cannot continue.
Jadi macam baik motor lah. Kalau dia lepas undur. Motor di depan.
Then after that, yeah, it is a good experience. It's like a joke that it happened. Then we prepared another one after fixed. Then we did the second one is the real one. And next, the third one, I hope you can install the sound sensor.
Now you know. Itu lain.
Yeah, many people in love. Yeah, we developed many type of circularly polarized antenna. If you want to learn how to develop the antenna, you can also learn from my laboratory. And I got many patents relating this circularly polarized antenna for mobile satellite communication or for the sound. And okay, it is our system, ground segment, and here for the UAV. Yeah? And here the flight control system, yeah? Like UAV asked me about the autopilot system, and here for the CPSAR. CPSAR is composed by mainly is image signal processing, chop generator, and the RF system. Here is composed by FPGA, PC, and ADC, and other memory and any system. And here for the navigation, we also install the IMU, GPS, and other also some information like the speed, velocity, or speedometer. And here we put many information because we want to connect the navigation information and the pulse information. We transmit pulse and we need to receive in the same time the position of our aircraft. Because then later we must mapping. Mapping. Disperse with position. Disperse and with position. So we need to save the information, then we process it. And it is our system for the HPA, high power amplifier. And we already developed the RMK company, and now we are submitting it with the MMU staff. And we already developed and made a very compact system. And I hope we can make some experiment later in Malaysia. And the spec here, the size is very compact. If you make by yourself, maybe it's very big. Because we're working in L-band. L-band is low frequency and the system is big. And because we must reduce to be less than 20 kilogram. If big, it's more than 20 kilogram, we cannot put in my UAV. Okay, and the power is 50 watt. 50 watt means we design for less than 1 kilometer. And it is the RFC. We insert here the chirp post, then we transmit and switch here RHCP or RHCP. Okay? Then after scattering, then we receive together here the simultaneously RHCP and LHCP. Then we process here and you can get the IQ data for the RHCP and the IQ data of the LHCP. Okay? Also, to be full polarimetric, full polarimetric. Like this one, we transmit left-handed and we receive together. Left-handed, right-handed. Then we transmit right-handed and we receive left-handed, right-handed. And here's full polarimetry. Right now, if you cannot get a full polarization, the data is garbage. You cannot get it. Impossible is full polarization. Because from full polarization, you can get many information. It's not just the phase information. You can also find the change on the relationship between the object and the polarization. And you can get more precise information. It is the chirp pulse, the real chirp pulse is like this one. In phase and quadrature. Then it is developed by MMU, for the chirp pulse generator and image processing. Oh, ADC, DAC, now, and my student also involved in this development. My student, Suto-san. I hope we can make the exchange during to develop this sensor. Then here is the chirp pulse generator. The real chirp is like this one. It is from our output when the bandwidth is 50 megahertz. 50 megahertz, and on the ground is around the resolution is around 2 meter. 2 meter. In L-band, in L-band, 2 meter. If you want to increase your resolution, you need to expand your bandwidth. But our system, we can expand until 150 megahertz. So around 1 meter, less than 1 meter, we can do that. But why 50 meter? Because ITU, International Telecommunication Union, they decided if we want to work in L-band, 1.275 gigahertz, the center, they just allow 50 megahertz. In urban area or close urban area. But if you fly in far away from the urban area, with the far away from the area with many electrical devices, maybe you can use 150. So we can adjust using this. And here's the real bandwidth, the frequency domain here. There is 50. 50 we here is compared to the maximum intensity is minus 3 dB. Minus 3 or half. how far? 50 megahertz. Okay, this is the system. And we also developed the FPGA to process the image of the sun. First is the range compression, then azimuth compression, and you can get the image. Here's the raw data, range compression, and azimuth compression. You can get. I think MMU also developed the process like this one in the PC base. And our case is we work in FPGA base. Okay, yes, this one. I hope we can process more faster using FPGA. For one chip of JAX1, if we need just 1 minute process. And it is a comparison, we make a simulation. Here's the linear polarization and here's the circular polarization. And you can get, it is the linear polarization. The effect of the foreshortening and the shadowing is very high. But you can use circular polarization. I hope more clear. Yeah? You can get the information on the shadowing area. Or you can reduce the foreshortening area. Yeah? Use the circular polarization. Okay, and other, if we use the polarimetric, why we use the polarimetric? Yeah? Maybe you can compare, like I'm already explained the tilt angle. You can get, the response of the one object. For example, you can turn it from 0 to 359 degrees, and you can find the spectrum in the angle, tilt angle spectrum, and you can get interesting. Yeah? For example, here 0 degree. You can find this is the scattering from the urban area. Yeah, and here from the maybe from farmer area, and then here forest. Yeah? Forest area. And if we turn 80 degree, disappear. And here's almost same. And here's almost same. Like this. So it means, the effect of the tilted angle is, give effect to our image. I hope you can, in the future, you can find the spectrum. Here's the tilt angle from 0 to 390 degrees, maybe like this. From one response. So you can get, this maybe this effect is the response from the pine forest. It is from the limestone or from the rock. From even the same rock, but maybe you can get, this rock is mixed with something. So you can get from this aspect. I hope you can read this, this aspect by using my CPC. Okay, this 80 degree and 0 degree, and you can find. Some part is same, but some part is different. If you can resampling here, for example, this point, the same point here, and you can find the space. Maybe like DNA, this are DNA. Okay, this memory calculation is okay. I want to skip it. Maybe it is the real how to calculate the memory. It's not so difficult. Transmit and receive. And okay, it is it is another satellite now we developed to monitor the ion. this one. It is the GPS and it is our satellite. I give name Gaia 1. Gaia 1. And we move like this one and we monitor like this one, and the refraction. Based on the refraction, we want to get the information of the ion. Okay, I don't. Oh, still classified. Okay, I want to. Oh, this one, the standing. It is from GPS. Then we want to find the refraction here, and if we can use this information, you can predict the earthquake. Now I propose as 200 million yen for this. Like this one. We want to monitor this one. It is GPS, and we want to monitor. It is our satellite profiling. It is GPS system and like this one. We monitor like this one. It's moving. Oh, like this one. And it is very simple one. Simple one with the GPS receiver. Okay, just GPS receiver and you can get the information on the ion. And antenna we can develop by ourselves. Okay, if you have interest, so maybe you can discuss with me. Okay, I want to close and let's take lunch and we start from 1 o'clock.